6.1 is going to be about the law of sines. The law of sines is used to solve oblique triangles. Oblique triangles are triangles that don't have a right angle. So everything up until now has been about right triangle relationships. Everything we've learned so far is about right triangles. So what happens now that we don't have right triangles anymore? Here's what an oblique triangle may look like, right? It's just like any other triangle, except there is no 90-degree angle anywhere, and even some triangles may have angles that are larger than 90 degrees, right? So those are called the obtuse angles. Okay, so what we just mentioned is that the relationships among the sides and angles of right triangles are not valid for this type of triangles. So we need to create new relationships in order to work with oblique triangles. And those relationships are going to be called the law of sines. So you're going to be looking at a triangle defined with A, B, and C in uppercase, and those are going to be the angles of the triangle. Lowercase a, b, and c are going to be the lengths of the sides of the triangle. So the law of sines is the following. Lowercase a over sine of angle A is equals to the length of side B over sine of B, and it's equal to length side C over sine of C. What this means is that the ratio of the length of the side of any triangle to the sine of the angle opposite to it is the same for all three sides of the triangle. So those ratios are consistent. They're equal to each other within that triangle. And that really is all there is to the law of sines. Okay, it's very simple. Now, let's talk about how we come about figuring out the law of sines. The derivation of it is quite simple. You have a triangle ABC with angles ABC and sides A, B, and C as well. They're labeled that way, right? The side opposite to the angle has a lowercase of that same letter. But what we're going to do is draw this extra line that is going to be called the height of the triangle, right? So all of a sudden we create a new triangle, one in here and one here, and notice how these ones are right triangles. So what we can begin to create is some relationships. So for example, say that we define sine of B on this triangle using the SSA-No definitions that we know. We're going to get opposite over hypotenuse, so H over A, right? And then we can also do sine of A, which is here, and we get opposite over hypotenuse, so H over B. So we get these two ratios, right? These two definitions from what we know. But notice that they have something in common. They have an H in both of their definitions. So if we try to solve for H, we get the following. A times sine of B is equals to H, and B times sine of A is equals to H. So we're saying that whatever B length of B times sine of A equals to is some length h, but this is equal to this. So we can kind of ignore the height or the h and set them equal to each other, and we'll have A sine of B equals to B sine of A. And so let's move things around so that we can have the law of sines pretty much, right? So we can begin by dividing sine of B from both sides, and we get A is equals to B sine of A divided by sine of B. And then if we divide both sides by sine of A, we get the following. So A over sine of A is equals to B over sine of B. And thus, this proves part of the law of sines, right? We obviously don't have the relationship for C over sine of C, but we can do that by creating the same process that we just did, okay? Just rewriting the triangle originally a little different. So we would need to create another height from here to there, creating another right triangle within. Okay, so something like that. And then that would allow us to create another relationship and thus be able to come up with C over sine of C. Okay, so this is how we derive that relationship. So it's quite simple, so it's good to get in the habit of trying to understand where things come from. Okay, it makes it easier for you to remember it, and really you're not really trying to memorize things, you're trying to understand how they work. Okay, now let's do an example following the formulas from before, right? So this is the given information, and we're solving a side angle case, right? Where we're given a side, a measurement of an angle, and then another angle. The side is not in between the two angles, right? That is a different scenario. Okay, so let's kind of go ahead and start working on it. And the answer to that, we know one ratio, which is C over sine of C. That's the only information that kind of is given, the only ratio. And then here's this other angle, right? So let's go ahead and solve for that, plugging it in and solving for the missing pieces. Angle C happens to be 63 degrees, and make sure your calculator is in degrees whenever you're trying to solve this type of problems, okay? So this is the relationship that we have. Multiply sine to the other side, sine of 46 times 56 divided by sine of 63, and that's equal to A, whatever that length is. Okay, so plug it in the calculator and make sure that your calculator is in degree mode, because if it's in radians, it'll give you an answer, it just won't be the right answer. So if you plug that in and follow the directions that you're told at the beginning of the problem, right? Oftentimes they want the lengths to be rounded to the nearest tenth. You know, if you do get decimals, make sure you round to the nearest tenth, or whatever the directions tell you to do. So if you plug this into the calculator, you get that length A is equals to 45.2. Okay, so we can move that off to the side since we figured that part out. Okay. We can also figure out the last angle, right, the missing angle, by following the idea that all of the angles inside a triangle add up to 180, right? That's a given fact or known fact, right? So we know that A, B, and C has to equal 180. We know that A is 46. We don't know what B is, but we know that C is 63 degrees. And all of that has to equal to 180. Okay? 46 plus 63 happens to be 109. So B is the same thing as 180 minus 109. And B is equals to 71. Okay? So we have almost everything so far. We have this angle B, we have this measurement. The only thing we're missing is length B, right? So we'll figure it out by setting up another ratio. So B over sine of 71, and I'm going to use the given known ratio. So 56 over sine of C, which is 63 degrees. So B is equals to 56 times sine of 71 all over sine of 63. Okay, so once we plug that into a calculator, we're going to get that B is equals to roughly 59.4 inches. Okay, so we have solved the triangle completely because we know everything about it. We know it's 3 angles and it's 3 sides, and that's all that we need to know, right? That's all there is to a triangle or solving a triangle. Now let's solve the following. You are given angle A is 50 degrees, angle C is 33.5, and B is equals to 76. Okay, and we're told to round to the nearest tenth. So whatever value we get for the length of the sides, it's going to be rounded to the nearest tenth. Create any type of triangle and label it. Okay, it's going to be easier for us to see what's going on if we have some kind of picture. So draw a picture and then just label things. Okay, A, B, and C. And we're not assuming that this is a right triangle. Okay, this is 50 and this is 33.5, and we got that B is equals to 76. Okay? This is one of those cases called ASA because we're given an angle, a side in between, and then another angle, right? So angle, side, angle is the case that we're dealing with right now. So first thing to do is to find the third angle, right? And we use the fact that A, B, and C add up to 180. So A is 50, B we don't know, and C is 33.5. 50 and 33.5 happen to be 83.5, and then B is equals to 96.5. Okay, so we found that information using the fact that all angles add up to 180, right? Now we can begin by using one of the known ratios. So we're going to use 76 over sine of 96.5 in order to start building and finding the other missing pieces. We could begin with trying to figure out A, so sine of 50. Okay, so this is us looking for A, so that's that ratio. But then we're going to use the same thing when we're looking for C, right? We're going to say 76 over sine of 96.5 equals to B over sine of, I'm sorry, looking for C, not B, 33.5, right? Here we have sine of 50 times 76 over sine of 96.5 equals to A, and on the right side, solving for C, we have sine of 33.5 over times 76 over sine of 96.5, and that's equals to C, right? So we used the first angle and side length combo, right? Because we only had two angles but no lengths, and we have a length side but we didn't have an angle, but we figured it out first by doing the ABC adding to 180. So that's why we're using it first for pretty much everything now. So solving for A, we get that A is roughly 58.6. Since we don't know the units, we really don't add the units into our solution, and that's okay. We get that C, and when we plug it into the calculator, roughly is 42.2 units. So we have the three angles, and then we have three sides, right? Now we're going to talk about what is called the ambiguous case, and when you're given a side, and an angle. Okay, so you're given two sides and an angle opposite to one of them. Can we solve the triangle? Right? You may think, well, yeah, of course, we just did one example of that. Now, but what is the difference with those previous examples is that one of them was the side was given in between two of the angles, and in this one we're going to look at a possibility, right, that there may be one triangle, two triangles, or no triangles, right? So the ambiguous case, like we just said, may result in different scenarios: one triangle, no triangle, or two triangles being graphed out of that information. So the number of possible triangles, if any, is going to depend on h, the height, where h is defined as length b times sine of a, right? So given some information, right, we draw up a triangle. We have an angle and we have a side and a side. So what if one of the sides is shorter, right? Like we just drew it up here. And of course, if this is not long enough, it doesn't close the shape, right? And you should know that a shape that doesn't close is not considered a triangle, is not considered a shape itself, right? So that's the case we're looking at with the scenario, right? There are several cases that follow from there. So the first one is one triangle, right? There could be one triangle, and that comes when A is greater than the height, right? So remember, h is the height here in the middle, right? And also A is larger than B. So if this is longer than this, the only way for this to close and be a triangle is for this to go all the way over here and close the shape, right? So one triangle is formed. That's one case. The second case is that we have a right triangle, okay? And that happens when A is the same as the height, okay? So obviously here would be h, and the height of the triangle is the same as the length of A, and in which case we would have a right triangle, and we know how to work with those, but we can also apply the law of sines to it if we needed to, okay? Now the other cases are going to be no triangle, right, when A is shorter than the height. You have a dangling side that is not long enough to close the shape. So we can't have a triangle, okay? And then there's the case where two triangles happen, okay? So this case is when A is greater than h, right, is longer than the height, but it is not longer than B, right? So you could end up with two triangles. One triangle is going to be the shorter looking triangle that looks like this, okay? And then the other one is going to be the one on the right side. So two triangles can come about, and we would have to give information for both of them. And notice that they share one side. This is the side that they share. So you would have a known length between those two already. So those are the four cases, right? One triangle, one right triangle, no triangle, and then two triangles. Okay? Let's do an example using the law of sines. Given angle A is 43 degrees, length of side A is 81, length of side B is 62. We want to round the length to the nearest tenth and the angle measurements to the nearest degree. So the best thing to do is to draw a triangle. Okay? Make a little sketch for us to look at, right? So many ways to kind of begin this problem. So one thing that we can notice is that A is greater than B. So that happens when there is one triangle. Okay? So we know that we're at least going to have one triangle. So we can at least look forward to solving one triangle. That's all that I'm trying to say. So we'll draw something, label it, and then go from there. Obviously the picture is not required. It just kind of helps you see where things are and which things you have solved for, right? So this is 43. The length of B is 62. And length of A is 81. So we have a ratio that's given, which is this one right here, right? We have A over sine of A, and that is 81 over sine of 43 degrees. And that's what we're going to use to come up with everything else. Okay? So let's get it. We have B to be given as 62 and then sine of B. Okay? Multiply both sides by sine of B. So sine of B times 81 over sine of 43 is equals to 62. And remember, this is what we're solving for in this setup right now. So we're going to multiply sine of 43 to the other side. So we'll have 62 times sine of 43. And then we're going to divide both sides by 81. So we have 62 times sine of 43 over 81, right? Plug that into the calculator and we get the following. Sine of B is equals to roughly 0.5220. So we're not going to leave our final answer like that. This is just to get an idea. So you have to be kind of careful. If you get a number here that is greater than 1, then you should think sine of any angle can only be between -1 and +1. So if this is a number that's bigger than 1, then you would understand that there is no angle that can give you that measurement. So you would have no triangle if that was the case. Alright? So here's where we have to get kind of smart about things. Notice if we think back to the unit circle, sine is positive in the first quadrant and the second quadrant. Okay, so there are two angles between 180 where sine of B gives us 0.5220. Okay, so if we do sine inverse of both sides, we get that B is equals to 31 degrees. Okay, so here is 31 degrees. So we get that angle B is 31 degrees. But then also it means that this angle here would give us 52.20. So we would have to do 180 minus 31 to get the other angle, which is 149. So if you add this 149 to what we already know inside the triangle, which is 43, we get something like 192. And we cannot have that be a possibility, right? So 149 is out of the question because it exceeds the sum of 180, right? So the only possibility is that B is equals to 31 degrees, okay? The possibility that B could be 149 is out of the question because it happens to be greater than 180 when you add it to the other angles, okay? So that's important. We need to consider that information. So this is 31 degrees. Then, given that, we can find the third side by adding the information, right? We have 43 plus 31 plus C equals to 180, right? And so those two combined give us 74. And when we take it away from both sides, we get that C is equals to 106. Okay, so we found another angle, but then this one was found after we figure out that B was only 31 degrees, right? We have to think about the different possibilities now. Okay, so what are we missing? We have B, we have A, we are missing length side C. So let's move that aside for now. Make some room. So C is the same thing as C over 106 equals 2. We're going to use the given information or the given ratio, which was 81 over sine of 43. Multiply to the other side, and we have 81 times sine of 106 over sine of 43. And we get that the length of side C, and we'll make it smaller so it doesn't look like an angle, after we plug that into the calculator, is going to be roughly 114.2 units. Thus, we found the missing pieces, right? We found the missing angles and the missing side. Okay? So hopefully that makes sense. The next example, we're doing the same thing. We're solving a side-side angle triangle using the law of sines, given the information that A, or angle A, is 75 degrees, side of A is 51, and length of B, or side B, is 71. So let's begin. Notice that A is less than B. So that happens when does it happen? It happens when there is no triangle or there are two triangles. Right? There could be two triangles, but we don't know yet. So we have to kind of get going and solving for something. So let's make it a triangle just to label things. You know, it doesn't necessarily mean that because we draw a triangle that there's actually one. So this is just to label things. A, B, C. This is 75. We know length A to be 51, and B is equals to 71. So let's solve for angle B. Okay, so we have 51 over sine of 75 is equals to 71 over sine of B. So we'll do the whole cross multiplication in order to solve for angle B, which is the unknown in this problem, this setup. So multiply sine of B to the other side, and at the same time we can multiply sine of 75 to the other side, and then divide both sides by 51, and we'll have sine of 75 times 71 over 51. So remember, we mentioned at the beginning that A is less than B, so this is the only case that covers, or the possibilities are that there is no triangle or there are two triangles. So we don't know yet. So whatever we get from here is going to help us decide that. So B is equals to what? Roughly, if we plug it into the calculator, we roughly get 1.34. So sine of 75 times 71 divided by 51 comes out to be roughly 1.34. So here's one hint, right? Because sine can never be greater than 1, then there is no angle B that you could plug in here that gives you 1.34. So this means that there is no angle B, right? Or there is no triangle for the given measurements, right? So pretty much no solution, right? There's no triangle for that, okay? And that's it. In the next example, we're going to talk about the same thing, side-side angle, but here we're given angle A is 40, length of side A is 54, and length of side B is 62. And again, we figure out that A is less than B. So here we have another possibility of having no triangle or two triangles. So we don't know. How can we kind of determine that? So let's make a triangle just to label things like we've been doing. Okay, so here's A, here's B, and here's C. We were told that this is 40, here is 54, and here is 62. So let's talk about the height. We said that if A is greater than H, but A is less than B, this means that there's two triangles. So let's figure out H. H is given by B times sine of A. So 62 times sine of 40 comes out to be what? So it comes out to be roughly 39.85. Okay, so is A bigger than H? And the answer is yes. A is less than 62, or A is less than B, therefore we're going to have two triangles. Okay, we're going to have two separate triangles that are possible given the information. Okay, so what that means is that this shape that we just drew is going to look something like this. Where this is the A measurement, which is 54, and this is also 54. Okay, so if we make the triangle a little bit larger, I think it's going to be better for us to see it. So this is B, A equals 54, this is C, so this is what that means. A equals to 54, so how do we begin this problem? Because clearly we now have a lot to work with. Okay, so the way that the book does it, okay, is that we know the ratio, right? The known ratio is A over sine of A, okay? Or 54 over sine of 40, okay? So we're going to use that, and we're going to start by taking care of B, angle B, because it's the opposite side length that we have. We don't have anything else. So we have the opposite, which is 54, but then we also have the opposite of length B. So that's what we're going to solve for first. Okay, so this is going to be gone, and we're going to use that information. So we know 62 as the length of side B, and we don't know what angle B is. So cross multiply things, we'll have sine of B times 54 equals to 62 times sine of 40 degrees, and so sine of B is equals to 62 times sine of 40 over 54, right? Here is where we do the sine inverse on our calculators. And we get the following. So roughly we get B is equals to 48 degrees. So we do the same thing as we did before with checking the unit circle thing, and we know that sine is positive in the first quadrant and in the second quadrant. So here's the first angle, and then here is the second angle, which we find by doing 180 minus 48, and that comes out to be 132. So what is going to happen now is that we get to break this problem into two separate problems. Okay? This triangle that we found has two angles B. We're going to have to relabel things and call this B1 and this right here B2, where B1 has an angle of 48 degrees and angle B2, which we just found here, is 132, right? 40 plus 132 does not exceed 180. So that's why we're allowed to have this big angle here, and this one is relatively small. So let's make things a little bit more clear. So here's one angle, or one triangle if you will. So the idea here is that the outermost triangle is one triangle, which is here, and then the innermost, which is the smallest triangle here, is shown right here. Okay, they share the angle 40, right? They have this length here, which is 62. However, they have a couple things that are different, right? And is that angle B here, which is the difference between the two. So we'll change the colors so that one of them is a different color than we're solving for, so that you can see what I'm talking about. Okay, so we are missing length of C and angle C. So let's go ahead and solve for it. One of the given ratios was 54 over sine of 40. And well, before we even do that, let's solve for the missing angle, right? So we know that 40 plus 132 plus C1 has to equal 180. So 40 and 132 happens to be 172 plus C1 equals to 180. Therefore, C1, whoops, that's C2, sorry. C2 is equals to 8 degrees, right? So we figured that out. Now we can use the ratio of 54 over sine of 40 equals to length of C2 over sine of 8 degrees, right? So sine of 8 degrees times 54 over sine of 40 equals to C2, the length of C2. Once we plug that into the calculator, we get that C2 is roughly 11.7 units. And that would leave us with everything already for that triangle here, right? It's kind of small, oops. But that's 8 degrees for that angle, 132, 40, and then the missing side length is 11.7 units. So that was all for this guy right here. Now for the bigger purple triangle that we have here on the right side, we'll do the same. First begin by figuring out C1, so 40 plus 48 plus C1 has to equal 180. So 40 and 48 happen to be 88. And C1 is equals to 92. So C1 is 92. That was one thing we were missing, but we're also missing its opposite side length. So we use the same ratio of 54 over sine of 40, and we're looking for length C1, and we use sine of 92 multiplied to the other side. Sine of 92 times 54 over sine of 40, and that equals C1. And so C1 is roughly 84 units. Okay, so there are two possible triangles for the given information, and then if we kind of use the information about the length of h and try to figure out whether a is bigger than h or not, that will allow us to see whether we have two triangles or no triangle at all. And that was the case here, that we had two triangles. The bigger one outside is the one being displayed here, and then the smaller one in here is the one displayed in blue. Okay, we were able to figure out the second measurement of angle B after we found the first one. We subtracted it from 48, and since we got an angle that made sense, and when I say it makes sense means when we added it to the given angle 40, it didn't exceed 180. So we were able to use it to create both triangles. Okay, and so that is everything for using the law of sines to figure out whether you'll have one, two triangles, or no triangles at all. Alright, thank you for watching.